Okay, this class is physical chemistry class, and in this class we will mainly deal with thermodynamics. Thermodynamics is composed of two different words, thermo and dynamics. Thermo means heat, and dynamics means flow or motion. So in this class, over this semester, we'll deal with how heat, a type of energy, changes during a certain type of process, how they change from one type to another kinds of energy, etc. And this field, thermodynamics, started early 1800 when the Industrial Revolution occurred. As you remember, during Industrial Revolution, people invented power engine or the train run by burning fossil fuels. So they basically changed heat energy to motion of train or like different kinds of energy. So we'll also deal with that kind of energy conversion or energy change in this class. So let's first start chapter 1. Chapter 1, the title of chapter 1 is Properties of Gases. So there are three main kinds of phases. As you all know, there is gas, there is liquid, and solid. We'll get back to that point again in the following slide. And among three different phases, we'll mainly deal with gases, the main properties of gases. So in chapter 1, we'll first deal with perfect gas, or we call it ideal gas too. I believe that all of you have learned about perfect gas or ideal gas during elementary chemistry class, right? So we'll review those properties of perfect or ideal gas, states of gases, gas laws, or also, since this gas law or ideal gas law is a reference model for all gas behaviors, we'll briefly introduce kinetic model of gases, which also corroborate this ideal gas behavior. Okay. But gases around us is not ideal gas, right? So they are real gases. Okay. So real gases are quite different from ideal gas. So we'll learn how they are different, what kind of properties are different between real gas and perfect gases. So we'll first consider molecular interactions. What are they and how they are different between real and perfect gases. And also we'll deal with van der Waals equation. You might not be familiar with this equation. This equation basically describes the behavior of real gases. And we'll finally introduce principle of corresponding states. Okay. So overall, during this class, until chapter 6, we'll learn about all these basic properties for thermodynamics, basic concepts, basic terms, etc. And we'll apply them for various kinds of changes. I mentioned that we'll deal with changes of energy, right? So we'll learn about physical changes, and also we'll learn about chemical changes. That's the goal of this class during this semester. So as I mentioned, there are three different phases of matter. So let's introduce each of them. First, there is gas. So let's see the properties of gases. Gases can fill a container. Everybody knows that, right? And they take on the shape of the container. Okay. And the important property of gas molecules are their particles or gas molecules are very widely separated to each other. Right? The distance between each of gas molecule is quite far from each other. Okay? So interparticle interactions are minimal. It's very small. Even for ideal gas, we totally ignore them. Okay? We'll get back to that point again. Okay? How about liquid? Liquid does not fill a container. Unlike gas, it cannot totally fill a container. But it takes on the shape of the container, right? And comparing gas and liquid molecules are very closely spaced. Their interparticle distance is quite small compared to gas molecules. How about solid? Solid does not fill a container, okay? And they do not conform to the shape of the container, right? And also in terms of interparticle distances, they are very closely packed. So there are these three different kinds of phases, and we'll mainly deal with gas molecules. So let's introduce perfect gases. I believe that all of you know about this, right? So we'll consider a hypothetical perfect or ideal gas. Because we mentioned hypothetical, because there is no perfect gas in this world, right? So we just imagine there is perfect or ideal gas. Okay? It's basically gas, so it has properties of gas molecules, right? So their interparticle distances are quite large. Okay? Another important properties of perfect gases are described as follows. Okay? As you see, the first property is same as other type of gas molecules. The speeds of particles increase as the temperature is increased. That's quite obvious, right? Because as you increase the temperature, that will increase the kinetic energy of these gas molecules. Then that will increase the speed of gas molecules, right? And second property of perfect gas is that the molecules are widely separated from one another, with the only interactions being with the side of the container and other molecules during infrequent collisions. Okay? So since this is gas molecules, basically perfect gas, so interparticle distances are quite large. So the only interaction, which is described here, only interactions inside of this ideal or perfect gas is the interaction between gas molecules and the side of the container. We basically ignore the intermolecular interactions between gas molecules for the definition of perfect or ideal gas. That's the most important property of perfect or ideal gas. There is no intermolecular interactions, such as dipole-dipole interaction, van der Waals interaction, etc. There's no interaction whatsoever. Okay? That's the most important properties of ideal gas. The next slide is about states of gases. So what exactly is state? State is something here, which is here, the physical state of a substance is defined by its physical properties. State is just state. What kind of state of a gas molecules have? Look like that. Okay. If you want to describe the state of gas molecules inside of a certain container, you might consider its temperature, pressure, volume, etc., right? So those kind of properties, temperature, pressure, or volume, is physical properties. Okay? So those physical properties basically define the physical state of the substance or gas molecules. And there are basically 4 different physical properties which can define the physical state of a substance. So 4 of them are as follows. Volume, gas molecules have volume, right? And amount of substances, number of moles basically. Pressure, gas molecules have pressure, right? And temperatures. And many scientists over the last few hundred years have found that empirically or experimentally they found that among these 4 variables, all you need to know is 3 of them, any 3 of them. If you know any 3 of these 4 variables, the 4th variable is automatically fixed. Okay? So if all you need to know is 3 of them, then the 4th variable is automatically determined. Which means that these 4 variables have a certain type of relationship, right? So that relationship is called equation of state. It's basically equation which describes the state, physical state of a certain substance. Okay? So, equation of state can be described generally as follows. P equals F, a certain type of function of temperature, volume, and number of moles. So if you have information about these 3 variables, temperature, volume, and number of moles, that will automatically determine the pressure. Okay? For example, as you all remember, for ideal or perfect gas, P is equal to V nRT over V. Right? PV equal nRT, which is ideal gas law, right? So ideal gas law is a kind of equation of state. Oops. Sorry. So let's define each of these 4 physical variables. Actually, not 4, some of them. First is pressure. How can we define pressure? Pressure is the amount of force divided by specific area, right? P is equal to F over A. Everybody learned this, right? From general physics class or from high school class, right? So pressure is basically originated from force, right? Exerted on a certain area, right? And that force comes from countless collisions of gas molecules to the walls of container. Remember that there is interaction between gas molecules and the wall of the container. Right? So those interactions or those hitting or collisions of gas molecules to the wall is basically the origin of pressure of gas molecules. And depending on the units, pressure have different kinds of units, such as Pascal, bar, atmosphere, torr, etc. And we'll use some of them for specific cases, right? Especially the SI unit, the standard unit of pressure is Pascal. So 1 Pascal is defined as 1 Newton per square meter. Okay? Pressure exerted by gases. Let's consider this figure here, right? Let's assume that there is this kind of containers and gas molecules are stored in these two separate containers. And there is wall between these two containers, and though this wall can be moved by pressure. Now let's say that on the left side of this container, gas molecules have high pressure. On the right side of the container, gas molecules have low pressure. Okay? Then, since these gas molecules have higher pressure than this side, this wall, which can be moved, will move to the right. Right? That's obvious, right? Until the pressure on both sides are equal. Right? If the pressures of these two separate containers are equal, then the wall would not move anymore, right? This condition, when the pressure of both sides are equal, is called mechanical equilibrium. Okay? It's equilibrium in terms of mechanics, because it's basically because of this equal pressure, the wall does not move. Okay? It's very simple. Right? In this slide, we basically define what mechanical equilibrium is. It's the state where two different sides basically have equal pressures. Okay? Then how can you measure pressure? There are several ways or several devices used to measure pressure. One device, which is shown here, is called barometer. It's basically a certain liquid inside of this U-shaped glass tube, right? Usually we use mercury, liquid state mercury. So let's see this figure B. Inside of this tube there is gas molecules, and on this side of the tube it is exposed to atmosphere. And the location, the height, position of the liquid mercury is as follows, like here and here, right? From this atmosphere, atmospheric pressure exert onto the liquid mercury, right? And that pressure basically pushes this liquid mercury up to here, right? Because of this pressure, the mercury arises to this height, with height h. So in this case, pressure can easily be calculated by this equation. P is equal to rho GH. Here, rho is density of this liquid material, here mercury. G is gravitational acceleration constant, and h is the height of this liquid. The reason why this equation holds, I believe that you guys have learned this from general chemistry class. Okay. It's very simple, actually. Let's see. So we define the pressure P is equal to F over A, right? Force divided by specific area, right? And in this case, the force is basically gravitational force, so which should be equal to mg, mass of the material, gravitational acceleration constant. Right? And mass is equal to density times volume, right? And if you denote the area of this material, here in this case mercury, area as A, then the volume should be equal to area times height, right? Area times height is volume, times G. Okay. So we got the expression for force. So if you put this into here, to the definition of pressure, you can easily get rho G H, right? So if you know the information about the density of the material, liquid material, of liquid, mercury, you can easily calculate the pressure by using this equation. Okay. Next physical variable is temperature. Temperature is a property that describes the flow of energy. What that means? By experience, we all know that heat or thermal energy flows from high temperature to low temperature side, right? Everybody knows that, right? By experience. On a cold winter, we feel cold, right? On a hot summer, we feel hot, right? Because heat energy basically flows from hotter to colder side. So temperature is the indicator of the direction of the flow of energy. What direction? Basically from high temperature to low temperature. Okay? So let's consider similar figure here, as you saw from the definition of pressure. There are two compartments same, right? In this case, the left side, the gas molecules have high temperature. On the right side, gas molecules have low temperature. And there is wall here. In this case, it's not movable wall. On the other hand, the wall is diathermic wall. Diathermic means through this wall, energy or heat can be flowed, can be transferred through this wall. So let's consider this kind of compartments. Since gas molecules on the left side have higher temperature than the right side, the energy flows from left to right, right? Until it reaches this state, when both sides of the containers have same temperatures. If both sides have same temperatures, then the energy flow from left to right stops, right? There will be no energy exchange between these two compartments, right? Because temperatures are same. This state of equal temperatures or no energy flows between these two compartments are called thermal equilibrium. We learned mechanical equilibrium when we introduced the concept of pressure, right? For the definition of temperature, we introduced the concept of thermal equilibrium, right? If the temperatures are same on both sides of the object, that they are in thermal equilibrium. Okay? Seems quite obvious, right? From the concept of thermal equilibrium, we introduce the first law of thermodynamics. It is a law, and the first law is called zeroth law of thermodynamics. It seems quite obvious if you read it. So let's read the zeroth law of thermodynamics. If A is in thermal equilibrium with B, and B is in thermal equilibrium with C, then C is also in thermal equilibrium with A. That's obvious, right? There's three different objects. If A and B are in thermal equilibrium, and B and C are in thermal equilibrium, then C and A are also in thermal equilibrium. That seems quite obvious, but since it is obvious, it is the law, okay? Zeroth law of thermodynamics. The importance of zeroth law of thermodynamics is that it basically justifies the concept of temperature and the use of thermometer. We know what thermometer is, right? Thermometer is the device which can measure temperature, right? From the definition of zeroth law of thermodynamics, it basically justifies the use of thermometer. What does that mean? Is that let's assume that from this diagram, object B is thermometer. Okay. So if object A and B are in equilibrium, in thermal equilibrium, and B is thermometer, then thermometer would have a certain measure for object A, right? And let's assume that this thermometer is in thermal contact with object C. Okay? And then if the measure of B thermometer is same, basically the measure of thermometer of object C is same as A, then we can say that object A and C are in thermal equilibrium, right? So we can basically use object B as thermometer, which can measure the temperature, right? So the zeroth law of thermodynamics basically justifies the use of thermometer. Okay? And for temperature, there are also many different kinds of units: Celsius, Fahrenheit, Kelvin, etc. But in thermodynamics, the basic temperature unit is Kelvin. Okay? So we learn what thermometers are. So there are many different kinds of thermometer which can measure the temperature. Right? You can either use the height of liquid, because a certain liquid have a regular manner in terms of expansion of their volume or height. So we can basically measure the height of the liquid, the position of the liquid, to determine the temperature of a system. Okay? Or we can use the change in gas volume, or we can use variation in electrical resistance in wire, etc. One thing to note is that temperature is not heat. We define temperature. Temperature is a measure of energy flow from what? Like direction, right? From high temperature to low temperature, energy flows. Right? But heat is a kind of energy itself, right? So you should not misunderstand between these two different concepts, temperature and heat. Okay, this section is about kinetic model of gases. So in previous sections, we learned about ideal gas behavior, right? Ideal gas laws, 3 different limiting laws. And from these 3 different limiting laws, we got the ideal gas equation, right? The equation of state, right? And ideal gas law is true for only ideal gases, right? Real gases do not follow that law under normal constances. They are true, the law is true only at a certain limit when the pressure is really small. Although this ideal gas law has this limitation, it is a very good model or reference for other types of theory or models. This kinetic model of gases is one kind. So we didn't really, right? This ideal gas law, we got it from 3 different limiting laws: Boyle's law, Charles' law, and Avogadro's principle. All 3 of them were empirical or based on experiment, right? We did not really derive it. Right? There are actually 2 different ways to derive this PV equal nRT. One of them is from this kinetic model of gases, and the other is based on quantum mechanics and statistical mechanics. So we can easily derive this PV equal nRT. And let's see how we can do that. So let's briefly introduce this kinetic model of gases. What is that? What is basic assumptions to describe this model? And let's derive this kinetic model of the ideal gas law. Okay, let's use the whiteboard. So, as described in the next slide, kinetic model basic assumptions. Let's go back to the slide. Second. So let's consider first the basic assumptions. It's very simple. Kinetic model of gases is we just consider gas molecules in some kind of container. So gas molecules, they are doing random, never-ending motion. They are just moving randomly in a container. And second assumption is molecular size is negligible. Although there are size of molecules, right? We just ignore them because we consider that the interparticle distance or the distances the molecules travel is really large compared to the molecular size. And the third assumption for this kinetic model is that they are doing elastic collisions with each other and also with the side of the container. They are something like hard spheres. So if they hit with each other, they are doing perfect elastic collisions. They're just hitting back. Right? So based on these 3 basic assumptions, we'll describe the kinetic model. Okay. All right. Okay. As I just mentioned, for kinetic model, we're basically considering gas molecules inside of a certain container. They are moving, right? So here shows one gas molecule. Okay. Let's assume that this gas molecule moves in this direction, right here, like this, and collide with this wall of the container, and go back like this. Since third basic assumption of this kinetic model was these gas molecules do elastic collision, right? They will just hit at this point and go back, right? Simple. Let's assume that the velocity of this gas molecule is v. Okay. And we can easily divide this velocity, the vector property, into two different components, right? If you assume this direction is x and this direction is y, then we can have Vx like this, right? Okay. And this direction is Vy, right? What would happen if this gas molecule hit the wall and go this direction, right here? Since this collision is totally perfectly elastic collision, the total velocity would be same, right? So this would have, although this is small, okay, the total velocity would be same as before. It also can be divided into Vx and Vy, right? What would be the difference between this and this gas molecule? The other things are same, right? Only difference is that the Vx has the different opposite direction. Original gas molecules before colliding the wall had Vx to the right, right? But after colliding the wall, Vx has the negative side because it is the opposite direction to the original gas molecule, right? So let's derive the relation from these relations, okay? So let's assume that this gas molecule travel this distance over small amount of time, delta t. Okay. Then the distance this gas molecule travels would be velocity times times, right? Okay. So the distance this gas molecule travels would be Vx times delta t, right? 정말 작아. Okay. This was a bit smaller. Okay. So distance a gas molecule travel is Vx times delta t on x direction, right? Although we expressed this in 2 dimensions, it is actually in 3 dimensions, right? If you consider z like this, right? And if you assume that the area of this YZ plane is A, okay, then the molecules inside of this volume would hit the wall, right? So the volume would be area times distance, right? So A times Vx times delta t. Here we introduce the concept about number density. Number density. Number density is defined as the number of particles inside of this volume V. Okay? So if you have the number of moles n, total number of particles will be n times Avogadro's number, right? 6 times 10 to the 23rd, right? And since number density is number of particles per volume, okay? This is the number density. Okay? So then, how many particles would be here in this volume? That would be same as number density times volume, right? So number of particles will be V and A times A Vx delta t. Okay. This is the number of particles inside of this volume hitting the wall. Okay. Then let's go back. Let's calculate the total momentum change. Total momentum change. So momentum is mass times velocity, right? So total momentum change of the total number of particles. Okay. How can you calculate it? So for individual particle, one gas molecule, momentum change would be, if it has mass m, originally it had velocity of Vx, and finally it has velocity of minus Vx. So the total change in absolute value would be 2 mVx, right? For individual gas molecule. And we want to calculate total momentum change of total particles inside of this volume V. Then we can easily multiply this by this. Okay, just write it down. V over NA AVx delta t times 2mVx. Okay? But the thing is, we have to put 1 over 2 here. Because the particles inside of this volume over this time interval delta t have a chance, 50-50 chance to move this direction or this direction, right? It's have 50-50 chance. Okay? That's why we have to put 1 over 2 here to calculate the total momentum change. Okay? So if you arrange this, you can easily get the expression here as total momentum change is V and M A Vx squared delta t. Okay. All these calculations are in the slide, so you can follow the slide. So we calculated the total momentum change. Okay. Then let's calculate the force, F. So force is defined as the momentum change divided by delta T, right? From general physics class. So we get NMA Vx squared over V. Okay? Now we can calculate the pressure since we have force. Okay? Pressure is defined as force divided by area. Right? So if you delete this area, you get an mvx squared over v. You get the expression about pressure. Okay? Alright. Let's delete this part. Here we have expressions about velocity square. And in a container, in a volume V, the gas molecules would have distribution of velocity. Some molecules would move faster, some molecules would move slower, etc. Right? So we need to express this velocity as an average by using this bracket. So this bracket means average velocity. Okay. Since we are basically dealing with these gas molecules in 3 dimensions, if I draw this again, the gas molecules move, the average velocity in each direction, like Vx, Vy, and Vz, average velocity of each of them should be same, right? Because it is average, right? So if you sum all these 3 average velocity, Vx squared, Vy squared, and Vz squared, it should be same as basically Vx squared times 3. We can denote it as c squared. Okay? Then if you put this c, this Vx squared here, then we can have this expression between P and V as 1 over 3 and mc squared. Okay. Not right. Actually 3v. Okay. So from this relation, we get PV equal 1 over 3 n c squared. C is average velocity. So if C is equal to 3r t over m square root, if you put this here, we would get PV equal nRT. Okay? Then why this average velocity can be expressed like this? That's actually quite simple. I mentioned that gas molecules in a container would have distribution of velocity. Some molecules move faster, some molecules would move slower, right? That kind of distribution is called Maxwell distribution. The scientist James Maxwell basically established this kinetic theory of gases, and the Maxwell distribution can be expressed in analytical equation. It's very actually complicated. If you look at the slide, you can see that the basically all this. Basically, Maxwell distribution of gas molecules is something like this. Fv is the distribution of speeds of gas molecules, and x-axis is v. So in a container, normal container containing gas molecules have this kind of distribution of velocity. Some molecules move slowly, some molecules have average velocity, some molecules move faster, something like that. This is called Maxwell distribution. And this Fv, distribution of velocity of gas molecules, can be expressed analytically as something like this. 4 pi m 2 pi RT v square. Very complicated, right? It's not really complicated. You can actually derive these relations using some basic equations. And how can you get c square, the average rotating scale velocity? Basically, I express this as average velocity. To get some number for average, you can easily get it by doing integration, right? To get the average velocity square, you can easily integrate v square velocity of each of gas molecules and distribution, right? Some molecules have small speed, and molecules with small speed have this distribution. Some molecules have this speed, etc. We just multiply by this velocity square and the distribution and just integrate all of them. Then we can get easily the average velocity square, right? If you do this, you get this, as I just showed in previous, before I do this whiteboard. If you put this number, you get PV equal nRT. Okay. Right, so this is the end of kinetic model theory. One thing to note is this expression here. Velocity of gas molecule has relation basically between with this temperature. As we increase the temperature, velocity increases. We already have considered this relation a few times before, right? It's obvious, right? If you increase the temperature, kinetic energy of gas molecules increase, and that will increase the velocity of gas molecules. Okay. So this is the end of section 1.2. Okay, now we'll cover section 1.2. As you see here, the title of section 1.2 is Gas Laws. So in previous section, we introduced the concept or definition of ideal perfect gases. And perfect gases follow several laws. So it followed. So as you might remember, there are three different laws: Boyle's law, Charles' law, and Avogadro's principle. And although real gases also follow these laws, they only follow these laws under limiting cases. That's why we call these three laws as limiting law. So here limiting law means that it is also true, it is only true for a limiting case when the pressure approaches zero, when pressure is really small. Which means that, or if pressure is really small, which is same as the case where volume is really large, inter-gas molecule distances are really large. Because it's the case when the gas molecules behave very similarly to ideal gas. So from these three limiting laws, we can easily derive perfect gas equation, equation of state, remember? And also we'll introduce mixtures of gases, which means that other than these three laws, there are another important properties of gases which deals with mixtures of gases or fraction of gases. So let's introduce one of these three laws one by one. The first law is Boyle's law. So all these three limiting laws are basically empirical laws. Many scientists, including Boyle, Charles, or Avogadro, did a lot of experiments by themselves, and they found out that gas molecules follow these relations or these laws. So this scientist, Robert Boyle, who was an experimental philosopher in the early years of the Royal Society, he did a lot of experiments using gas molecules under vacuum, etc. And he found that to a very good approximation that for a constant amount of gas at a fixed temperature. So he fixed temperature and the amount of gases, and what he found was that pressure and volume of that gas, the pressure times volume, is constant. Or we can say that pressure is proportional to 1 over volume. Okay? Pressure is inversely proportional to the volume, or volume is inversely proportional to pressure. What he actually did was something like this. You remember this kind of instrument, right? To measure pressure. So he could change the pressure using some kind of instrument. Using this kind of shape, you can easily measure pressure. Remember? We can easily measure pressure if you know the information about the density of this liquid and the height of this liquid, right? So you can easily measure pressure. You can easily measure volume. So he manipulated this instrument by changing volume and pressure, and what he found was that if you multiply pressure by volume, the multiplication is constant, approximately. Okay. It's very interesting law, right? Since pressure times volume is constant, their relations can be plotted as follows. If you plot pressure as a function of volume here, since P times V is constant, their relation looks like this, as represented as hyperbola. Or if you want to represent it more easily, if you plot pressure as a function of 1 over volume, since pressure is proportional to inversely proportional to volume, their relation is linear, right? So these kind of relations, pressure versus volume or pressure versus volume, is called isotherms. Here, iso means same. Therm means temperature. So basically, same temperature. When we describe Boyle's law, we maintained temperature constant, right? So it is basically at the same temperature. Right? The relation between pressure and volume at the same temperature. That's why we call this relation between pressure and volume as isotherms. Then, how can you rationalize this Boyle's law? How can you understand this relation between pressure and volume? Let's assume that we have an ideal gas in a container, and the pressure of ideal gas is P, volume is V. What if we reduce the volume of the container by half? If you reduce the volume from V to V over 2, what would happen to the pressure? You can easily imagine that since the volume is now half of the original volume, twice as many molecules would strike the walls of the container. And this striking or hitting the wall is basically the origin of the pressure, right? Remember, right? When we define the pressure is defined as force divided by specific area, right? Since the volume is now half compared to the original volume, basically twice as many molecules are striking the wall. That's why we would have twice of the original pressure. Then P times V, or 2P times V over 2, should be same, right? Following the Boyle's law. Okay. Next limiting law is Charles' law. Same. It is also empirical law. So this scientist, Jacques Charles, a French physicist, did a lot of experiments using gas molecules, right? What he found was that the volume of a fixed quantity of gas at constant pressure is proportional to its temperature. Or similarly, we can describe this Charles' law. The pressure of a fixed quantity of gas at constant volume is proportional to its temperature. So if you fix the pressure and the amount of molecules, the volume is proportional to its temperature. Okay? So at constant pressure, volume is proportional to the temperature, or we can easily describe the relation like this. At constant volume and at constant number of moles, V is proportional to temperature. Or similarly, at constant volume and at constant number of moles, pressure is proportional to temperature. That's Charles' law. Okay, then let's plot this relation between volume and temperature, or pressure and temperature, as we did for isotherms. Okay? So here we plotted volume as a function of temperature. Okay? At constant pressure and at constant number of moles, they are proportional to each other, so they have linear relations. Okay? And these different lines represent basically different pressure. Right? So this relation between volume and temperature is called isobars. All these lines are called isobars. Iso means same, remember? Bar means pressure. Here, we basically fixed the pressure constant, right? The pressure is constant. Pressure is safe. That's why we call this volume versus temperature relation as isobars. Okay. Similarly, when you fix volume and number of moles, we can have relation between pressure and temperature, right? And they should be proportional to each other. They have linear relations. Okay? And each of these lines represent different volume of gas molecules. And these relations or these lines are called isocores. Core means volume. So we fix the volume and we'll get the relation between pressure and temperature. That's isocores. Let's rationalize Charles' law. Why at constant volume and number of moles, why volume is proportional to temperature? Why the pressure is proportional to temperature? It's described well here. As the temperature is increased, the average speed of the molecules increases. That's obvious, right? Because the kinetic energy of gas molecules increase. So, increased speed of molecules increase the number and force of the collisions that the molecules have with the container's walls. Gas molecules move faster than the number of collisions. The strength of the forces would increase. That's why it increases the pressure of the gas molecules as a function of temperature. That's quite easy, right? Easy to understand. The third law, well, here it is, principle, is Avogadro's principle. Avogadro's principle is described as here in this sentence, that the volume of any gas is directly proportional to the number of molecules at constant temperature and pressure. If you fix both temperature and pressure, okay, volume is proportional to the number of moles. Actually, it's a very important principle because people, before Avogadro found out this principle, people did not believe it. Because at that time, a famous scientist who was Dalton insisted that every matter consists of only atoms. Okay? So they didn't know anything about molecules. You know what the differences between atoms and molecules, right? We all know that now, that all the materials consist of molecules, right? But at that time, Dalton was much more famous than Avogadro. So most of the people believed Dalton's basically hypothesis about atoms. But people, including Avogadro and Charles, did a lot of experiments. And they found out that they cannot explain the experimental phenomenon only by Dalton's hypothesis. So Avogadro insisted that matter, especially gas molecules, consist of molecules, not atoms. But people did not believe at the time. After, like tens of years later, after Avogadro died, actually, one of his students figured out that this is really true, and after those years, people believe that Avogadro's principle is true for all gas molecules. So we introduced three different limiting laws: Boyle's law, Charles' law, Avogadro's principle. So if you review all three of these, Boyle's law is described as here, right? At constant N and T, P times V are constant. Charles' law is if N and either V or P are constant, then P or V is proportional to temperature. Avogadro's principle is from here that when temperature and pressure are constant, volume is proportional to the number of moles. If you combine all three of these relations, three laws, we can easily get these relations. P times V equals to constant times N times T. If you denote this constant as R, you can get PV equal nRT. Ideal gas law, right? And as I mentioned at the beginning of this section, this is limiting law. It is true for ideal gas when there is no intermolecular interactions. But it is not true for normal, real gases. But it is true for real gases when pressure approaches zero, when the pressure is really small, or when the volume is really large, when the interparticle distances between gas molecules are really large, then we can possibly ignore the interactions between gas molecules. That's why it is true at this limit. Okay? So we got this gas constant R. Depending on the situation, it has different. Wait. Sorry. I'm very sorry that I'm rang. So depending on the unit, it has different numbers for gas constants R. Right? Usually we use this number 8.3145 joule per Kelvin per mole because it is SI unit for gas constant. Okay, so we learned three limiting laws. If you combine all three of them, we get perfect gas equation, right? A kind of equation of state, right? So we can plot the relation between these three variables, pressure, volume, and temperature, right? If you fix the number of moles, then we get these three-dimensional plot or some kind of surfaces, right? Pressure, volume, and temperature. And from these relations in three dimensions, we can easily get three of these limiting laws. For example, let's consider Boyle's law. Boyle's law, the pressure times volume is constant, is true when the temperature and number of moles are constant. So we fix the temperature. We fix the temperature here. We fix it here. If you fix the temperature, then we get this hyperbola, right? PV equal constant, which is isotherm, right? Similarly, we fix volume. We fix here. Then we get this linear line, right? Which represents pressure is proportional to temperature, which is isochords, something like that. Okay. Finally, let's briefly introduce Dalton's law, or something like the law. I already mentioned about this Dalton, which was a very famous guy. Okay? So, although we are not really going to deal with mixture of gases until chapter 4 or 5, let's briefly introduce the concept about mixtures of gases. So, when we have two or more gases are mixed together, how would we describe this system? Dalton's law basically describes these mixtures of gas behavior. The total pressure exerted by a homogeneous mixture of gases, total pressure, is equal to the sum of the partial pressures of the individual gases. Okay? So if you have a mixture of many different kinds of gases, there will be total gas pressure. That total gas pressure is simply the sum of partial pressures of individual gases. Okay. It's very simple. So total pressure of mixtures of gases is basically sum of partial pressures of each gases. Very simple, right? So if you have mixture, gases mixture, we can define mole fraction, or we call it X, small letter X. The mole fraction is defined as the number of molecules, specific molecules, as a fraction of total number of molecules. So mole fraction Xj for specific kind of species J is defined as Nj divided by N. Nj is the number of moles for species J, and N is total number of molecules, basically total number of moles of the molecules, right? So if you combine all of these mole fractions comprising the mixtures, so if you sum XA, XB, XC, etc., if you combine all of them, if you sum all of them, we'll get 1, right? That's obvious, right? And when you have gases mixture, we can define partial pressure of gas, partial pressure of individual gas, which is defined as mole fraction times total pressure. Okay? Partial pressure of species J is defined as mole fraction of J, Xj, times total pressure. So if you combine if you sum up all of these partial pressure, PA, PB, PC, etc., if you sum all of these up, you'll get this expression, right? Because the definition of partial pressure is like this. Okay? And remember that if you sum up all these mole fraction, which is equal to 1. So the sum of partial pressure is total pressure, as described by Dalton's law. So obvious, right? So when we have mixtures of gases, we can easily use this concept, mole fraction or partial pressure. But we'll not really consider the mixtures until chapter 5, so we'll get back to this point later.